Now let's talk about another prediction of general relativity that's been spectacularly confirmed just in the last few years: gravitational waves, or gravity waves. There was speculation about gravity waves right back from the beginning of the theory of relativity. In 1916, Einstein thought about the idea of gravitational waves. He used this logic. General relativity predicts that space-time is curved. If a mass changes its configuration or moves, then the curved space changes. And Einstein recognized that that information must somehow propagate through space-time. And most plausibly, it propagates at the speed of light, 300,000 kilometers per second. He made an analogy to Maxwell's equations, where if you wiggle a charge, either an electric or a magnetic charge, you create an electromagnetic wave that moves outward at the speed of light. The problem is, with Maxwell's equations, with electric and magnetic charges, you can have a dipole. You can have positive and negative charges equally. There's only one charge of matter. There's no such thing as a negative mass. So in gravity theory, there are no dipole moments the way you would have an electrical or a magnetic dipole. And a changing dipole is the easiest way to create an electromagnetic wave. That's how we do it with our technology and make radio waves, for example. So the failure of this analogy with electromagnetic waves led Einstein to doubt the existence of gravity waves, and he pretty much set them aside. In 1936, 20 years later, he wrote with Rosen a paper that pretty much concluded that gravity waves could not exist because this wave would create a singularity, a place where the curvature of space-time would become infinite. Now, strangely, for a physicist as good as Einstein, it turned out he made actually several mistakes in the paper, and this paper was rejected. This was a shock to Einstein. This was actually the first time he'd ever had a paper rejected. He didn't even usually subject his work to peer review. It was just published without question because he was Einstein. Other physicists were left to work out that gravity waves could exist, and so their prediction was in the literature in the 1930s. However, they were not observed directly. In 1974, Russell Hulse and Joseph Taylor, two radio astronomers, used a clever method of indirectly proving the existence of gravity waves with pulsars. They discovered a binary pulsar, that is two compact stellar corpses or neutron stars that were so close together they were interacting gravitationally, and they showed that they were orbiting towards each other or spiraling into each other. They showed that the measured rate of decrease of the orbital period was exactly that predicted by general relativity, because some energy from the system was being lost in the form of gravitational waves. So this was indirect affirmation that gravitational waves existed, and it won them the Nobel Prize in 1993. Direct detection, though, would take longer, and it required the most precise physics experiment ever built. How do you detect space-time ripples? Because that's what a gravitational wave is. Anything changing, any mass configuration changing or mass situation changing will send and propagate signals out three-dimensionally through space-time, and they correspond essentially to space-time ripples. The little animation on the left shows some of the rotational and distortion modes of space-time ripples. Space-time is invisible. We can't see it. But when gravity situations change, space-time ripples will propagate in 3 dimensions at the speed of light. And so we just have to visualize the flexing of space-time as a gravity wave passes through. There are many vibration modes possible, not just the ones we see here. There are twisting modes, torsional modes, compression modes, transverse modes. All of these modes can occur at once. So how do we detect something like this? On the right, we see a little animation of the LIGO configuration. This is a huge experiment. Each of those 2 perpendicular arms represents a 5-kilometer vacuum tube laid out in a different part of the United States. There were 2 identical LIGO experiments because the signal is so subtle. Physicists had to be sure by the simultaneous or near simultaneous detection of the signal at 2 completely different locations. They had to see that to be convinced the gravity waves were real. So to detect these waves, these space-time ripples, light is passed along these 2 orthogonal vacuum tubes, each 5 kilometers long, and then recombined in an interferometer to see if the length of the tubes has changed due to the passage of gravity waves. So when a gravity wave passes through the Earth, It literally flexes space-time, which means it flexes the Earth, it would flex our bodies if it passed through us, and it flexes a large instrument like a 5-kilometer vacuum tube. But the flexing, the amount of distortion visualized in that flexing ring of space-time you see on the right side, can be smaller, is smaller than the size of a proton. So that's an incredible level of sensitivity, and that's why this was the most accurate physics experiment ever designed. Brilliantly, it was built at the cost of about $1 billion, and it succeeded in late 2015, published in 2016, with this system, the first detection of gravity waves from a binary black hole. Two black holes, one 29 times the mass of the Sun, another 36 times the mass of the Sun, combining, and as they combined, sending ripples of space-time cascading into space. It happened, though, 1 billion years ago, because these binary black holes are 1 billion light years away in the distant universe, in a far-off galaxy. And so these waves have been traveling through space and diluting through space as well for 1 billion years before we were able to detect it. You see in the map in the lower right the two locations, one in Washington State and one in Louisiana, of the two identical LIGO experiments. And given the direction of the origin of the gravity waves, the signal traveling at light speed arrived 7 milliseconds later at one location than the other. And that was allowing us to say what direction it came from. As these two black holes merged, some of the pure mass energy was turned into gravitational waves and released into space. This is a prodigious experiment. You see the sensitivity of it at the top, 1 part in 10 to the minus 17 meters. That was the amount of the deflection of space-time in this situation. And here we actually see the signals from LIGO Hanford and LIGO Livingston, and they are delayed one from the other by about 7 milliseconds. The crescendo you see is called a chirp because if you turned it into a sonic signal, it would actually be audible. The frequency, as you can see, rises from a baseline of a few tens of hertz up to a few hundred hertz, audible frequency range. This was the space-time ripple surge that was detected, showing that two black holes had merged and opening a brand new window on the universe. Think of it. In the entire history of astronomy, we've only observed the universe with telescopes, with optical telescopes for 400 years, and then in the last century with other forms of electromagnetic radiation. This is a non-electromagnetic radiation type of astronomy. It's as if we had gravity eyes and we're seeing directly mass, whether it's dark or visible, by the impact it has on space-time itself. It's an extraordinary experiment, and it opens up a new field of astronomy. LIGO, which is the acronym for Laser Interferometer Gravitational Observatory, will soon, when it gets more sensitivity, be detecting probably 1 black hole merger per week. It will also see signals from other compact objects merging, such as black holes with neutron stars or neutron stars with each other, and it in fact has seen some neutron star mergers already. Also around the world, other observatories are being built, so LIGO will not just be 2 instruments, but already 1 in Europe, 1 in Japan, 1 in India, and eventually 7 or 8 different gravity wave detectors, all working together to give even more detailed information on these situations in space. It's an extraordinary new form of science. And within a year of the LIGO discovery, the 3 architects of the project won the Nobel Prize in Physics. What is it like when black holes merge? If we could see it up close, this is what it would look like. All those optical distortions are real, the gravitational lensing of light. This is what it would look like if we had gravity eyes. So this is a simulation, a true astrophysical simulation of the gravity waves that will come out when those same black holes merge. So that crescendo we saw, the chirp signal, is the place where the black holes actually merge and coalesce, sending out that flurry of gravitational waves. And then there's what's called the ring down phase, as the merging black hole settles, like a pile of jello actually, and more gravity waves are emitted. It's a very particular trace or waveform, and that's why physicists were in no doubt that that's what they'd seen, because they'd simulated the phenomenon before they ever detected it. This is a new form of science, and it's only just getting underway. Here we see a diagram of all the possible gravity waves we might detect in the universe. And so far, we've only detected the ones from terrestrial interferometers on the right of this diagram. That is to say, gravity waves that have frequencies of tens or hundreds of hertz. The frequency of gravity waves, when black holes merge, for example, is inversely proportional to the mass of the black hole. So as the black hole is more massive, the frequency of gravity waves goes down linearly. And we know there are supermassive black holes in the universe. So on the left of this diagram, we see the much longer frequency or slower frequency gravity waves that we know exist when massive black holes merge. Galaxies, we believe, grew by mergers and acquisitions, by growing and merging together as the universe evolved. And since every galaxy has a black hole, those black holes must have merged, and so the signatures of merging black holes in galaxy cores should be all around us in the universe. We need a separate instrument to detect these because geological noise stops LIGO and ground-based terrestrial interferometers from detecting these very low frequency gravity waves. These are gravity waves that could have frequencies of hours or years for a single cycle of space-time compression and rarefaction. We actually have mechanisms proposed with space interferometers or pulsar timing, using pulsars as timing devices, they could possibly tell us about the supermassive black holes merging in the history of the universe. An incredibly exciting form of gravity wave astronomy that we're not even started doing yet, but it's what the future holds. So this is an incredibly new and very vibrant field. And as we finish this topic and leave Einstein, I want to let you in on a secret, which is Einstein never actually died.
Oh, hello, welcome. You look a bit surprised to see me. Probably thought I'd been dead for 60 years, huh? No, as you can see, I'm fit like a fiddle. But I should probably explain. Sit down, sit down. I first came out here after the war. Loved the place. I knew I'd come back one day. You know, all the attention got to be too much. Einstein, please be the president of Israel. Einstein, please sit on this board. Einstein, you need to talk to this group and that group and the other group. No time to think. So I faked my own death. Ha! What fun. My housekeeper made up a story about an aneurysm. I paid off my doctor to keep the secret, and the head of the funeral parlor. Instead of me in the casket, 3 big sacks of potatoes. So when I was cremated, French fries. Excellent. So I came out here on the train, in disguise. What scenery! The cactus, the big sky. Love the chimichangas. Love those biker bars. Such nice people. The only thing I really missed from New Jersey, the bagels. But I did get sick. Then I read about a place in Phoenix. They do cryonics. Put you on ice. Well, liquid nitrogen. They have a price for just the head. I could get a new body. But when they heard who I was, they gave me a special deal. So I freeze the whole thing. Excellent. Quite an adjustment. When they defrost me, so much has changed. Computers everywhere. Phones you can carry in your hand. I missed the Cold War. People went to the moon. Amazing. So I must continue my work, still looking for the unified theory, the one that brings together gravity and the other forces, my life's work. Oh, excuse me. You can let yourself out.
And that's the end of this module.